Hello and welcome to the Semi-Israel webinar series. I'm Lee Harrison. I'm from Siemens EDA. And in this session, we're going to talk about in-system test and how it's becoming a critical element to silicon lifecycle management. So in this session, what I'm going to do is walk through just an overview of SLM, what SLM is, what the market drivers are, what we're seeing out there with our various customers. I'm going to talk a little bit about the causes of these in-field failures that are driving the market towards SLM. I'm then going to talk about the various options there are in terms of technology to help address those in-field failures, and then talk about the solutions that we've been developing within Siemens EDA and Tessent. So first of all, silicon lifecycle management. So what is it? Why is it becoming important? So what we're seeing is an increasing need to be able to have visibility of the silicon health and functionality throughout the life cycle of your products, rather than just making sure that we're shipping good silicon at manufacture. So what this entails is not only being able to make sure that you have an extremely high quality manufacturing test, is the ability to be able to repeat that type of testing in system, in life, along with being able to look at various other elements of the silicon's health, silicon's environment. So coupling DFT testing along with monitoring infrastructures, whether that's structural monitoring, parametric monitoring, but generally everything that comes within the functional operation of the silicon when it's in its end product. And then taking that information and data that we collect during the monitoring and testing, and bringing that out to the outside world, whether that's processing that data at the edge of the silicon or bringing that off chip to a cloud-based environment, where we can do deeper analysis, optimization, and looking at being able to predict the future in terms of what's happening with the silicon. So really opening up your silicon to be able to have a huge amount of analytics throughout the life of the silicon within its natural product environment. So what's really driving this technology and these requirements within the industry? Here is an example of statements made by a number of large data center providers, and how the ability to increase the server life, the server active life, by a number of years will massively reduce the cost of building these systems and supporting these systems. So for example, if we can extend the life of a data center server from 4 to 5 years to 6 years, or 40 years to 6 years, we can massively improve both the environmental aspect of having these large data centers, but also help with the overall kind of life expectancy of them, making sure that these data centers are working efficiently for longer. So overall, really optimizing the use of the silicon that's out there. And what are we looking at doing to achieve that goal? Well, obviously, manufacturing test quality is key to that. So the extremely high manufacturing test quality, but the ability to have the flexibility to update test pattern content once the silicon has left the manufacturing and is in its natural environment, to be able to rerun those test patterns, and to update and continually update that test pattern content throughout the life of the silicon. And in some cases, have the ability to add new tests. So for example, if during the life of the silicon you have units that identify unique faults that are not testable with the current test pattern configuration, you can add new tests to be able to capture those type of defects. Also, to be able to run this level of testing as part of the periodic maintenance, and also to be able to do full diagnostics when you do actually have a piece of silicon that goes down. So being able to do full diagnostics and analysis without actually having to remove the hardware from the data center itself. So all of these features and capabilities really go towards achieving that goal of enabling data center providers to reliably extend the life of their hardware by 2 to 4 years. Technology also applies in the automotive market. So in automotive, we're really focused on functional safety, preventative maintenance, and again here, being able to test the silicon in the field really provides the ability to monitor and predict the health of the silicon over the life cycle of the product. So here we're able to use the data that we generate through these this SLM environment to be able to predict how your vehicle's silicon is behaving, what the health of it is, and if there's any preemptive maintenance that's required. And there again, I say looking at using this technology as a safety mechanism, being able to run these technology during the startup and shutdown of the vehicle's electronic systems, and also requirement there to be able to do it in a time period that fits with the various standards that are out there. In this case, the ISO 26262, which defines a time requirement, the fault time tolerant interval, which is when you need to be able to run these tests to identify any failures that occur. And again, the advantage here of being able to update the test pattern content to really improve the testability and to aid that silicon lifecycle management throughout the lifetime of the vehicle. So what sort of faults are we trying to detect with this in-system test technology? So I'm sure everybody has seen the bathtub curve before, and where we're really targeting are the two areas: the early life failures and the wear out failures. So obviously with a very high quality manufacturing test capability, adding lots of new fault models, looking at providing forms of stress testing, enables us to reduce the amount of those early life failures because we're removing those during the manufacturing process. And then with the SLM technology, being able to monitor at a higher level the health of the silicon throughout its life cycle, we're able to look for those random failures, plus also the aging failures. So as the silicon starts to age, we can use our SLM technology to really look at the overall health of the silicon throughout its life cycle, and start to be able to predict, based on the data that we collect, when the silicon is going to fail. So really looking and being able to do predictive maintenance, predictive analysis on the overall health of the silicon. And going back to the point I made earlier about why we're looking to do this with regards to the data center type products, is having a high level of confidence in the health of the silicon as it ages over time means that we can keep that silicon in service for longer than we have been doing up till now. So having that visibility gives us the ability to gain every last usable piece of time out of that silicon before it needs to be replaced. So in-system testing isn't a new technology. It's been around for some time in the form of logic-based. But now we're introducing the ability to run deterministic test patterns in system. Let's just take a look at the comparison between the two technologies and see what the pros and cons are for both. So if we compare logic-based to the ability to run deterministic in-system test, test quality for sure is going to be a lot higher when we're running deterministic test in system, because we're able to use the same ATPG patterns that you use for manufacturing. So the test pattern quality is going to be a lot higher than what you would typically get with logic-based. Again, test time, because we're using deterministic test patterns, we're able to achieve a smaller window in terms of test time as we would do with logic-based, which uses a random test generation. And then on the test pattern content, again, as I said, we've got the ability to fine tune and change the test pattern content during the life cycle of the silicon, whereas logic-based, being random pattern generation, is very fixed and is not easy to change and update. So having that flexibility to be able to change and fine tune the test pattern quality really, really helps. In terms of implementation, in most cases, if we're implementing in-system deterministic test, then we would be reusing exactly the same DFT infrastructure as we would be using for manufacturing test. This isn't always the case for logic-based. Logic-based has some additional requirements in terms of X bounding and making sure the design is partitioned correctly to achieve a good logic-based implementation. So being able to use exactly the same manufacturing infrastructure reduces the overall effort required for the implementation. But all this doesn't come for free. The only challenge we have with the in-system deterministic test is we need to provide the actual test pattern data. So this has to be stored somewhere within the system, whether it's on chip or off chip on an external memory, and then streamed into the chip. We do need memory capacity to be able to store that test pattern content. We do see a lot that the type of systems that our customers are designing today typically have large amounts of memory on board. So doing that tends to not be too much of a challenge, but just be aware that in terms of using deterministic in-system test, there will need to be the data content stored. So if we look at the overall product offerings from Siemens EDA and Tessent. So as I said, in-system test has been around for quite some time. We've had a product out there in the market since about 2016 called Mission Mode. Mission Mode is our in-system test product, which enables you to effectively configure and load test data sequences for your logic-based and memory-based architectures, and enabling them to be able to run in system. The configuration data can be changed, uploaded, and controlled via an APB subordinate bus. So your in-system test controller Mission Mode will sit on an APV bus infrastructure, so that you can use an embedded CPU to deliver the configuration content for your various test structures. There is also the option to use the mission mode IP directly, so reducing the complexity of the system and not needing a CPU to manage it. So we have what we call a DMA access. But essentially, whether you're using the DMA access or whether you're using the CPU, all of the data will be delivered via the IJTAG network, and it will set up and control your logic-based or memory-based infrastructure. Just a quick note on manufacturing test product SSN, because I'm just going to talk about SSN in the next couple of slides. So just in case you're not familiar with SSN, SSN is our manufacturing test network product. So SSN is a packet-based scan delivery system where we can basically deliver all of your ATPG test pattern content over a simple bus structure. This really kind of improves and speeds up and reduces the complexity of your scan infrastructure on your chip. And then using that SSN infrastructure, we can move to the Tessent In-System Test product that was released back in November. So Tessent In-System Test is essentially it's a superset of mission mode, and what it supports all of the mission mode content that I talked about in the previous slides, but with the addition of being able to deliver full deterministic in-system tests. So full ATPG coupled with the SSN network that I just talked about. To achieve the speed requirements of SSN, so obviously delivering high-speed ATPG test patterns requires more bus speed than typical IJTAG. We support AXI. So in addition to the APV interface that was there with mission mode, we have added an AXI subordinate interface. So you can now deliver your test patterns at the same speed as you would deliver your SSN at manufacturing. So if we compare the two products, so Tessent Mission Mode is applying data over the IJTAG network. It supports the APB infrastructure, whereas the new Tessent In-System Test product also supports full SSN, so connection to the full SSN network, and to meet those speed requirements also has support of AXI. So if we jump into the detail, let's take a straightforward scan architecture. This is SSN, so you have 4 blocks in your design with an SSN infrastructure. Tap controller is there to basically apply the configuration for your scan infrastructure. We insert the in-system test controller. So that's inserted between the tap controller and the IJTAG and SSN network. Within the in-system test controller, we now have the interface to SSN. So we're able to drive SSN directly from the in-system test controller. We are still able to control the IJTAG network. So this is still a requirement to drive all the configuration and set up all of your design in the various test modes. And then the control mechanism here is through a subordinate interface. This can either be APB or AXI if you want the full speed capability. Driving that bus network, we typically see customers using a dedicated CPU, and then somewhere on the system there will be the memory that is holding the ATPG pattern data. As I said, the ATPG pattern data could be stored on chip, or if you don't have the capacity on chip, which is most likely given the size of the ATPG data, we've got the capability, because we have the bus infrastructure, to be able to pull that data from an external source, whether it's through a functional interface or a direct memory interface. So it's quite possible to store your ATPG data off chip and be able to pull that in from the chip itself. So in terms of what I said as in-system test being the superset of mission mode, so it still supports all of the functionality supporting logic BIST, memory BIST, and the various other features. But now with the support for full deterministic test patterns, we have this capability of being able to stream the patterns over the AXI bus, and then within the in-system test controller, there's the various buffering required to be able to cope with the delivery of that test pattern content. So just quickly on the AXI bus configuration. So it's a full AXI bus compatibility. It can be added to a full AXI bus infrastructure if you have that on chip. So here's an example where you typically have your in-system test controller, a CPU that's controlling the management of the test patterns. You can have your on-chip memory for paging the data, and then you can have your off-chip memory that's accessed through, in this example, a PCIe bus to be able to pull that data on chip. So, so typical functional bus infrastructure used to be able to manage all of that test pattern content. The IST itself, so the IP, here's just an example of the I/O that you would typically see when implementing that. So on the left-hand side there, you've got the pins that you would expect for an AXI4 interface. And then on the right-hand side there, you can see that we've got the connectivity to the IJTAG infrastructure within the chip, the SSN infrastructure within the chip, and the various other control signals. So when you implement your IST within your chip, this is the sort of pinout you would see for your the IP that you implement. I mentioned diagnostics. So there's several levels of diagnostics you can do with the in-system test controller. So it is possible to do full detailed diagnostics as you would do on an ATE, but also typically used is the more less granular diagnostics, which is essentially looking at the various cores within the design. Because you have an SSN-based design, you have multiple cores, and using what we call on-chip compare, we can basically run the ATPG patterns in system and determine if you have any failures, which cores those failures actually are in. This gives the ability of being able to give a level of diagnostics, but without having to shift and extract all of the diagnostics data off chip. So typically you would use this level of diagnostics first to understand if you've got any failing cores on the chip, and then you may go back and do a more detailed diagnostics of that that particular core independently. So to do that with on-chip compare, what we would do in terms of what test pattern content we would deliver the scan data, we would deliver the expected data, and we would deliver the masking data. So you've got all of the test pattern content being streamed onto the chip, and then the actual comparison is being done on chip itself. So this also means that you've got a nice solution where no data is actually being taken off chip unless you then move on to the next stage and do a detailed diagnostics. So in conclusion, with the market shift towards SLM, it is causing a greater adoption of in-system test methodologies. which is the driver behind why we've introduced the Tessent IST. We've got safety in mind. We've got all of the quality requirements in there as well. And there are many reasons that we're seeing that we see these in-life device failures. So having the capability to be able to address those is really, really important. And in terms of products, hopefully it's given you a very quick introduction to our Tessent In-System Test product, which is paired with SSN, our test compressed product, to give a complete solution to be able to detect in those test escapes in field. Thank you very much, and hopefully a useful session. And I think, yeah, thank you, and speak to you soon.